on your campus. So thank you for the opportunity to come and talk about work. So when Sean contacted me, I said, you know, I have very little direct industry experience. Are you sure you want me to be there? So I can tell you basically my interaction as an academic with industry. So my name is Javidi, and I have been at UC San Diego since 2005 as a professor in electrical and computer engineering. It's a little bit confusing. The two departments, computer science and engineering and electrical and computer engineering, used to be one department, and at some point in the 80s that separated into two. And the computer engineering program is the child of both departments. Neither one gave up the custody. So that's sort of where some of my these days research really sits in. But my own background is really where comes from the applied math part of an electrical engineering department. So I did my, I'm Iranian, so I did my undergrad in a technical university in Iran called Sharif, and then I came to graduate school at University of Michigan in Ann Arbor, thinking that if it's cold, at least I can ski. I had no idea how flat the middle of America was. And then after, I took a kind of a bit of a zigzaggy path. At the beginning, I wanted to do math, and my mom convinced me, hey, why don't you do engineering? If you decide to, you know, stay with just a bachelor degree with engineering, you will have more possibility of jobs than with math. And so that's what I did. I did a degree in electrical engineering, but I sort of never gave up the math love. So when I went to University of Michigan after a year, I decided, okay, I'm going to go do the thing I really love, which is mathematics. So I went and did a master's in mathematics, and I realized my mom was onto something. I can do the same thing in electrical engineering and get paid better for it. So I kind of moved back to electrical engineering and became an applied math / electrical engineering. I got trained in a field in electrical engineering that I'm sure all of you use on a daily basis. In fact, that's how we all start walking. It's called control theory. How many of you have been in the Science Museum down in Balboa Park? Okay. So I'll tell you, I don't know how many of you noticed this one item in the Science Museum. I'm not sure. Whenever I'm there, of course, my background is control, so I get very sad. I feel like the kids aren't playing with it enough. So I'll tell you and pay attention to it if you have not seen it. There is a large plate that has lines that are just like the ones on the wall you see, and it's hanging on chains. And the kids are asked to stand in front of this, raising one of their legs. And you stand, most of us don't fall. And then you you basically shake this plate. And as soon as it shakes, you fall. Because our eyes are so trained to keep our stability by keeping the view in front of you constant. So as soon as it goes to the left, you go to the right, and so on and so forth. So because you're one leg, you're more sensitive to this operation in your brain. So it's called a feedback loop, and that's how basically a lot of the systems keep the stability. So that's sort of the field that was born, I would say, out of different disciplines, but it was born out of the need to actually stabilize various unstable systems, the most notable one being airplanes. So there were a lot of engineers who did sort of more technical work building these flying devices, but they couldn't make them fly for very long and for long guaranteed stability through long flights. So this field is purely a mathematical model of the plane. So, and the people who actually the first time managed to build these stabilizers for our planes were really not the classic engineers who were very good with building systems, but they were pretty much mathematicians. So this field was born out of this thinking about mathematics. So this is one branch of electrical engineering that got really popular in the 70s. And then there is another area that, again, when I went to grad school, so I knew in undergrad this is what I want to do. And when I went to grad school, I learned about another area that is also, these days, is very, very close to my heart and something that I use a lot, called information theory. So this is another branch of electrical engineering that was born out of really purely thinking about an engineering system in a mathematical model of it. And that was the idea of how can you communicate? What constitutes information? How do you store it? How do you prepare it to be transmitted over, say, wireless, for your cell phones and such? So these two areas of research kind of caught my attention, and I thought, oh, I can do math, which is what I like, but I can actually have a more impact, far more impact, by translating that mathematics into actually building systems that use that math and that modeling to actually make change. So that's sort of when I went back to EE, and I sort of did a PhD thesis on the intersection of control theory, so how to use feedback systems to actually control the wireless systems that you see today. I always tell my students, I did my job talks talking about what can happen if we build better systems that can transmit data on a cell phone. And I constantly got these questions about why would I need my data on my cell phone? Do you need to check your email every minute of the day? And these days I'm like always looking at my phone, and I realized, oh wow, I was onto something. I didn't know. At the time I didn't even have a cell phone. So yeah, so the area grew, and I got very lucky. So what we were doing was very relevant at the time, and San Diego had a very good wireless group. So in 2005, I taught at University of Washington for a couple of years, and then in 2005, I got lucky. I got an interview at University of California, San Diego, up the hill from you guys, and I've been there as a professor. You start as an assistant professor, and you sort of prepare yourself as you go up. So now I have been there for 15 years, I guess. And things change. So wireless these days is a commodity. The companies have really squeezed a lot of the easy problems out by solving them. So nowadays I use the same techniques that I have used for wireless, but now in addition to the work that my students do in wireless, I am working on quantifying and sort of preparing information that you have for learning system and AI systems. So broadly defined, you see an image, and you would like, the system to, in an automated fashion, tells you what is the content of that image, whether it's a picture of a cat or a dog, or what is the background, what is the mood. You can make it more and more complicated, from the very easy task of just identifying the familiar objects in there, all the way to, can you say something about the context where this picture was taken, and so on and so forth. So for these systems, it's very critical to know how do you extract information, right? How do you actually look at pixels, which by far just an array of values. So a 512 by 512 image, you can sort of think about it as a very large vector. Every pixel gives you a value, so you can sort of think about a 512 by 512 dimensional vector. So you want to translate this giant mathematical object into a context of, let's say, easy tasks like cat or dog, or you can translate it to maybe more sophisticated context. So the same questions come about, and in particular there, the control part is through interactions with humans. So the first generation AI systems, the humans did a lot of the labeling. So the images are there, and you have mechanical Turks that just go, they get paid very little, but they just do label the information, and then you try to analyze these. Or if you're a Netflix user, for example, you as when you actually choose to watch a movie, you are labeling it as something likable for you or favorable for you. So this is the data that was collected in the first generation AI systems. In the more recent versions, you would like to use the same technology, for example, for interpreting medical images. Let's say you would like to speed up diagnosis of certain medical conditions based on medical images. Now, unlike the problem of cat and dog in internet images that all of us are pretty good at doing, at least I am not very good at looking at a medical image and tell you what is the content of that. And if you go to the doctors and ask them, you are interrupting them working on something much more important and critical. So in these systems, it becomes much more expensive to collect this data that has revolutionized the sort of new wave of AI. So it becomes really critical, what do you show a doctor? So you have very limited time to ask them questions. So now it really becomes important that you ask them questions that provide you with the maximum amount of information. So that interaction is like our interaction with that plate that I was saying. Your eyes are getting information in and trying to pick an action that is most suitable for stability. So again, these two fields come together to answer some critical information as what do you ask an expert? Or if you have different kind of experts, you have the general public, maybe I can say this is a round tumor. I don't know what that means medically. Maybe there is a medical school student who knows a little bit more about, oh, round tumors mean these possibilities. Maybe it's somebody who is doing residency in radiology, or the full-fledged, the best expert you have in the field. So if you have these kind of experts, how do you orchestrate machine learning systems in there? And then, so this is sort of what I got interested intellectually, started working on it back in 2010. And then something silly happened. I have an aunt who was telling me that she is going to grocery stores, but pretty much has given up buying anything that is on the lowest shelf. Her back hurts, she's not going to bend and look at the lowest shelf. And I thought, oh, this is an easy problem I can fix for you. I've got like a small drone this size, it's like a $50 drone. And I said, oh, it's very easy, I'll help you have this drone. It can take picture anywhere you want. You can look for your keys and stuff. So I started looking at this project as a completely side project for myself. And when I thought about it, I was like, where the drone looks is exactly the question you're asking, right? So again, you're basically orchestrating what to look and where to go deeper and fly closer and so on. So the flight path optimization for this drone ended up being, in the mathematical model, exactly similar to these research problems that I had been working on. And so I got interested in actually implementing some of the stuff that we're doing in the theoretical space and in software on actually these drones. And then for the first time, I had like students who were knocking on my door to do research in my lab because I was not doing equations anymore. I mean, I always had students who were interested in equations, but as soon as I became the drone lady, there were people who would just come and say, I'm first year, and I've heard you have drones. Can I do something for you? So then this grew to a whole slew of projects. And one of the things that we realized is my theoretician hat was very, very big for the reality, in the sense that I thought I can run these sophisticated machine learning algorithms on these drones. And the drones needed to be light, so the compute on them was not so sophisticated. So in the sense, if you're running a search, or like, for example, you do like Google, Translate. So for example, one of the easiest things I promised my aunt is that she will tell the drone, fly low, and it will do. So, and I thought, how hard is it? All of us have tried the Google Translate. You just talk to it, it understands. This is even easier because you're not going to talk to your drone about your philosophical issues. You're just going to give a few commands. It's going to be really easy. Running that command on a big computer in a data center somewhere in Iowa that Google is running can happen instantaneously. Running it on my drone, $50 drone, not so easy. So that's how I got closer to the hardware. because I realized those algorithms, those multiplications that for me as a mathematician is like, oh, you take two numbers, you multiply them. How hard is it? It's actually hard. It uses energy and it uses particular hardware that you're going to try to optimize. So this is how I got interested in this word machine integration in terms of computing. So again, so far, historically, we have seen this separation of hardware and software in terms of expertise. People started building generic hardware to do any kind of compute, and we thought of the hardware as an object that can multiply and add, and pretty much all of our thinking was, okay, if I have these building blocks, how do I think about building algorithms or such? So we sort of have gone two different paths. This came out of work of very famous people on computing. Where do you structure the memory? Where do you run your instructions? And that's like the sort of model of computation in old days. But now we're coming to a point that we're computing such amount of so much data with so much sophistication in terms of computational complexity that we need to really be coming back and say, this hardware has to be really closely thought of in that process. So that's the center that Sean talked about. So 2 or 3 years ago, a bunch of people like me, we think of ourselves as analytics people or theory people, got together with a bunch of people in truly computer engineering. These are people who build computing systems. We got together and said, we are working on similar problems from very different angles. Can we actually come together and bring our heads together and start thinking about these problems in a more systematic way? One of the reasons we were interested in this is that we were training students, and we noticed that the companies were more and more interested in students who can handle both. They know a bit of analytics, they can run some code to run the AI algorithm, but they are interested in running it on smaller devices. Tractor companies would come and say, I have compute on my tractor. Can you help me do AI, right? So this is sort of like where we see this sort of a new gap in the technology world, that we do analytics very well on infinite compute resources. We usually know how to structure compute for a set of generic computational tasks. Doing this together is what the center is formed to do. Our interaction with companies, and so the word center is not very generic, very specific, but at least in the context of a research center on a campus, it often means that your goal is to bring faculty together to address a problem that is not been addressed, but also to engage with industry to understand what is their needs that we as academics can address, and that conversation speeds up the innovation process, hopefully. So the center consists of faculty, then our students, some undergrads, a smaller number of undergrads, master's and PhD students, as well as industry partners. So the job of industry partners vary. They can come in and give us just advice on what things to work on in the next 10 years. They are sometimes interested in one little project. They will get a student to work on their project. So they decide how they would like to engage with the center, and we have a model of engagement with them. So that's sort of a long, sort of curvy path. So now I do actually computer engineering, and I'm sort of getting a lot more interested in how do you structure computing systems, for lack of a better word. They're not computers anymore. It could be your IoT device or your Apple Watch, but how do I actually arrange this so that's computing the most efficiently? And with that, I'll stop, see if there are questions, and then if there are not questions, I can give you a bit of a history on information theory, which is less known. Yeah.
So you say that you have industry representatives coming in and asking you questions about what they would like to know, so that they are prepared for what how they want to deal with the next 10 years. So what do they expect to be doing that we're going to see in the next 10 years?
So that's a very good question. So depends on their size, this question gets to be asked very differently. So if there's a very large company, they often have quite a lot of in-house expertise. So they sort of come to see the trends of what the academics are working on, see if they can see a good idea, and then they have quite a lot of in-house expertise to sort of think about we should move in this direction, that seems promising or not. If they're smaller, they come for specific expertise that we can provide that they do not have in-house. One of the main questions, so this is sort of the process. If you're asking what are the main questions that are on their mind, as I said, one of the things is how can we build systems that integrate the design of the algorithm. So you hire an analytics person and you have some sort of a platform, computing platform that you have either built or you have purchased, and you would like to put these together. So the one question that they're really interested is that a process to streamline this operation? Right now what happens is you bring an analytics or an AI person, they write the compute, some algorithm, this is all in software, and then you say, okay, I'm now going to implement it on this piece of hardware, and there's something called the hardware acceleration, that there are people who look at the algorithm and says, oh, this piece is a bunch of multiplication, I can run it here, this piece, and that's it. So you accelerate the software on the hardware and it gets implemented. Now, this means that the algorithm designer did not think about what the machine constraints were. So if you have a platform that is very resource constrained in terms of memory, that means that no matter how much the acceleration team has tried, that's the bottleneck. And maybe if they had talked back to the algorithm people and said, we don't have a whole lot of memory on this chip, but we can give you a lot of multiplications in parallel. So for example, for some of the GPUs, that's the mode. Then they would say, okay, I'm going to change my algorithm. Instead of store a bunch of things, maybe I will translate that operation of store in form of other operations. So this loop of going back and forth between hardware acceleration, which are computer engineers, and the analytics people is very expensive. And it's often a non-recurring cost for companies because they do this and then they're done, right? Like, what do you do? Do you fire these two teams? Do you fire half of them, right? So it's a non-recurring cost. So one of the questions that they have is that can we actually think about this process and automate that? Use machine learning to develop better ways of putting machine learning algorithms on the device. So that's one question. There are some other questions that are more abstract. So I don't know, how many people have heard of this adversarial machine learning? So this basically, if you show the classifiers that you're training on, let's say Google, let's say machines like a TensorFlow method or something, for let's say identifying stop sign from yield sign. And this is the big thing because there's autonomous driving and you're interested in cars that can drive and with humans and they have to interpret our traffic signs. You can build these systems and they do very well. These methods of learning these models that can do this sort of prediction is very successful. It's been very, very successful. But let's say, I would say 5, 6 years ago, people showed that you can change the stop sign by completely small amount of perturbation. So you can go and put like a cross on the stop sign, something that humans, we will not notice. And now you show the same picture to the same model and it says yield. So this is really dangerous, right? It's called adversarial machine learning because and of course in that, this cross was particularly designed to screw up the algorithm in terms of in the ways that it was developed. So it looks at the model and figures out its sort of weaknesses, and it builds models and examples that will fool this system. And one of the reasons this is doable is because this first wave of AI has been a compute only or data driven only. So you show the models millions of pictures of cats and dogs, and you ask them to identify, this. What they come up with is not necessarily interpretable for us. So it's not like we can look at this model, this neural network model that is very successful in telling you it's cat and dog, why it has this ability, where in the picture it looks, what pixels are important. Post the fact, you can then go adversarially say, I know it was looking at these particular aspects of the image a lot, so if I mess with those, it's going to get really fooled. So, but when we design the network, we don't know, we don't have interpretability. So a long-term goal for a lot of researchers in the AI community is to address interpretability of machine learning algorithms. If we understand how they come to the conclusions they come, then we can actually address this adversarial. Another issue that is again related to interpretability is fairness. I'm sure you've heard these methods have been used, for example, for allocating loan decisions, right? And they have been looking, and they are very biased in who they have, kind of giving these loans to, because again, we don't know what features of the data sets they look at. Something that I feel like personally affects me is they have shown that the STEM jobs, technology jobs, are not shown to women when you go browse, because we're a smaller percentage of the population in the STEM field. So it's figured out, oh, she's not going to click on this. So there's a lot of issues of policy and fairness involved, because we don't understand what aspect of my feature, all the information that it has about me as a consumer, as a traveler, as whatnot, it's actually extracting when it decides what ad it's showing me. Without that interpretability, there are all these questions of fairness that comes into that you would like to eliminate. You would like the model not to look at my gender, but looks at other attributes of my consumer behavior to give me an ad or not. So these are kind of interesting questions, all depend on this interpretability. I'm not sure if I can think of anything else in the long term that they have looked at, but if it comes to me, I'll say.
I have another question about your industry partners. Are they local, like San Diego? Are they regional, or are they from?
They're from everywhere, yeah. So the biggest supporters that we have tend to be the ones who have the longest history of collaborating with UCSD, some local and some international. So for example, with Qualcomm, we have had a very long and good historical relationship. So they're one of the supporters. There's another company called Leidos, again, and they have a lot of local operations in San Diego, even though they're a multinational company. Then there are companies that are purely like Honda or Toyota that we talk to them. And so yeah, so they're like, it varies. But yeah, often they come even if they don't have a particular operational presence in San Diego. It's easier for us to work with the ones who do, but even if they don't, sometimes they come for this. Yeah.
You were mentioning the difference between the computer engineering compared to electrical engineering or software engineering, and what the workforce is now looking for. Could you speak more about kind of the pros and cons of either doing computer engineering going one way or the other?
Oh, okay. So what I can tell you, even though I kind of grew up on the EE side of, let's say, EECS, electrical engineering and computer science, these days, you cannot get a job if you do not like to code. So I tell my students, sometimes my students say, I came to EE because I hate programming. And I tell them, let me break the news to you. These days, there's no company who will go and build any device without testing, simulating, emulating it in software. It's just too expensive to build a whole plane and then test it and it crashes, right? So you need to actually have tons and tons of not experiments, but simulated experiments in software, even when what you're building is as physical of a device as an airplane or as a car. Now, if you come more and more to computing, which is, building computers and building IoT devices that are, processing your information and so on, then you're more and more closer into the software domain. So I tell people software these days is like, proficiency in talking, right? Like, if you're an engineer, you will have to. So that distinction between hardware and software has sort of disappeared. Even if you're a purely hardware person, you end up coding a lot. And then I would say there is, of course, the sort of trends at the time. So like, sometimes there's more, it's like the software companies are doing better, so they're the ones who hire, and sometimes a bubble bursts, and, then it goes back to solid, good hardware jobs are more solid. So those trends are hard to predict and come and go. So I would say my advice to the students and in fact to my own nieces and whoever was asking and listening to my advice is try to see what you're good at, what you like to do. Hopefully there is an intersection in there, and then work in that area, because really you can't really predict, and we are generally better at what we do when we like it and we feel like it's impactful, and then we can actually be more productive than if you try to just cold hard. Like, as I said, I went to engineering because I wanted to make sure that I make a better income than a math person. But essentially that doesn't work out too much for too long. So my suggestion is try to do an intersection of these realities. As I said, these days there's a lot of need for companies that go from, especially certain sectors, they're not super like up to speed on AI, and there's a lot of interest. So a lot of companies are interested in people who can translate some of these algorithms onto their platforms that they have. In that sense, computer engineering is a very good field to be in. But so is if you're just a clear AI person or just build devices, that's also very, very popular. In general, it's a good time to be an electrical engineer and computer science major.
Thank you.
And I should say these days, and I agree with, robotics is also becoming more and more closer to our field, and so when I say all of these words, they're all inclusive in all of them. Anything else?
How small do you go, like power-wise, in your experiments?
Oh, power-wise?
Yeah. What sort of...
So I'm going to give you two answers. My own group, the smallest of these drones that I was saying, the $50 drones, and they go around 10 minutes of flight time.
So what about the smart,
Yeah, the total power they can last. The most expensive is their communication of the video to our handheld. All of our compute so far, because these are off-the-shelf drones, and that's exactly why I got interested in what it takes to put this compute from my, actually we run this on laptops. What would it take to run from the laptop or from the handheld device all the way to the drone? We have not been able to put it on the drone, so the compute is done on a phone, like a Google Android phone, or on my laptop or something like that. So in that sense, the expensive process is communicating the data so that I can crunch it up and then communicate it back to it. So it's not doing that heavy of a compute yet.
But in terms of computing, what's the lowest power that you work with?
Oh, that's what I'm saying. For my group, not so low.
Oh, yeah.
But then, as I said, the research center is 18 faculty. So there are faculty who are going really, really low power to the point that some of the machine learning algorithms can be implemented with new devices, with optical devices, and they go extremely low power I don't know top of my head what those numbers are, but if you can do compute in optical domain, the speed of light and optical communication is a lot faster, so they go very, very low. The problem there is you cannot reconfigure. Electronics are really good. You write a new code, you change parameters, you change numbers in software, so it's very easy to change that. If you've built a not mechanical, optical device to do the compute, you're stuck with those parameters, and changing it will require a lot of overhead. So that's sort of the trade-off in that space. But the interest is to go as low as optical.
What kind of partner has surprised you? Someone that you didn't think or expect to come to you, or they kind
the company?
kind of question that they approach you with that you were like, wow, I never thought about that before. Anything that kind of stood out?
So the way it works is it's the nature of running a research center, so maybe I should spend some time on that. So we got together as faculty, we said this is a critical point. We talked to a couple company contacts we had. For example, I had a former PhD student who was working at Qualcomm. My co-founder has a student who works at Google Brain. So we talked to them, said, oh, we're thinking about this. Does this sound like something that industry would care about? And they said, yeah, this is a very relevant project. And then after that, you are in this startup mode. You keep going to companies and say, this is what we're doing. So in that sense, we sort of are more, we are the ones who are selling the idea to them. So in that sense, it's not as surprising, I would say. So we go with this vision that you should care. So if they say they are, we're like, oh, okay. The surprise has been there were some companies that seemed they should care, but there were other reasons that they were like, there's like name recognition. They would rather give the same money to a university whose name is more like, I don't know, Stanford or Russell. So that part is maybe the surprising, that the subjective part more than the scientific part has been surprising the response.
So I'm actually kind of interested in the information theory and how it intersects with like big data, and also I thought that you had some association with information security as well on the flyer. So
yeah, so let me give you an answer to the second question because it's easier. So the center, we are interested in integration of compute and machines and security. We feel like security has been far ignored in terms of you build your machine and you put your compute on it and then say, what should I do? It's not secure. You add security, it's like always an afterthought. And again, in that design loop that the designer thinks of an algorithm, puts it on hardware, we want it, this is what happens. They usually bring a security team that looks at this and says, I'm going to encrypt the data and do this. So we were interested to actually think of algorithms that from get-go are secure. So for example, for the machine learning algorithms, so that's the stuff that I have worked on. It's only in the security of a physical system or an AI system. I've worked on these systems, but I'm not a security expert. So there are 4 or 5 other faculty in the center. In fact, in particular, my co-founder, who is a person who goes to IEEE security and privacy conferences. So the security work I have done is of the sort, you have a physical device like autonomous driver and you have put some machine learning algorithm on it. How can I make sure that it's actually robust to these adversarial samples and sort of. In terms of information theory, so how many people have heard of information theory? Okay. How many people have heard of the person who is believed to be the founder of information theory? Good. Oh my God, you guys are my friends. You want to mention the name?
The founder of information theory,
Shannon.
Claude Shannon. Claude
Shannon, right.
Claude Shannon. So actually, I should say I'm wearing many, many hats in my life. One of them, I'm on the board of governors of IEEE's Information Theory Society. And we just finished this massive project of a movie about Cloud eShannon. So please check, we're still, as an entity that has invested $1 million in this, we're deciding how to get distribution of it. It might be a showing in San Diego, but we are hoping to maybe the big distributors will pick it up and then it will be available. If not, it will be on YouTube. So please check on my website. There will be and it's a kind of like documentary, science documentary. It's been shown in like festivals and not. So and we in our community think he's just as big of a name as Einstein or or Turing, and it's a very sad fact that not too many people know about him. Some of it is that he just looks like a usual guy. He doesn't have some complicated neurotic personality that like they can make a Hollywood movie that would sell. He's just that he grew up in Michigan, actually very close to Ann Arbor, and went to University of Michigan for undergrad in mathematics, and then he went on to MIT. In 1948, he wrote a paper. He called it A Mathematical Theory of Information. And a year later, and this was at Bell Labs, so at the time, Bell Labs was the sort of the place for a lot of scientists to be doing research there. So he wrote this. It was a Bell Labs systems sort of report. A year later, University of Illinois published the manuscript and called it The Mathematical Theory of Information. And it pretty much set the ground for almost all technologies today that we think of as digital communications. So your cell phones, your digital TV, your email, anything you do. In fact, I cannot even imagine without his contribution what this would be. And the really fundamental thing that he proposed, and it got picked and got sort of changed the world, was the notion that information, the syntax, is not important when you want to actually communicate or store data, but it's how much randomness there is in the data. So all things that are unexpected are informative. So, for example, the weather in San Diego, we don't think of our weather forecast people as particularly informative people, right? Most of the time, it's the same weather, right? Why? Because we think, it's not, so we think, how hard is it? But if you live in the Midwest, where the weather changes every half hour, and then, the randomness contains more informativity in there. So he proposed a way of quantifying, when you look at an outcome, how much information there is. More importantly, he proposed how to present this with binary digits. So he said, okay, if something is more common, we should be able to represent it with small number of bits, because we all agree. So the weather's sunny, I might not ever tell you it's sunny. When it's rainy, with the low probability event, I come to you and say it is rainy, right? So we all do this. For things that we expect, we don't communicate. For things we do not expect, we build longer sentences. So he translated this in terms of how you actually can incorporate information. So this is called compression. So his paper was half about how do you represent information. So how do you actually get a signal? Before that, people were interested in communicating over, let's say, the telegraph channel or over the air. They would spend so much time about the air, electromagnetics. They were thinking about the physics of it. So what he did, he sort of separated himself from the physics and said it really doesn't matter how the signal goes. It's about how likely it is to see one option versus the other, 0 and 1. That's the bits. And for example, when you use your cell phones, the waveform, the shape of the wave, the electromagnetic wave that carries your signal is multiple versions. So you can think of 0 or 1. If you get zeros or ones, it looks at the shape of the signal. You don't actually necessarily bother about the physics of it. You just say, does it look like this shape or this other shape? So that's sort of like how half of the story is how you compress or represent information. The other half of the story, which is more mysterious, is that he said, now if I want to actually protect against sort of channel impairment, which is what people were doing, like I'm sending something over the air, there's going to be bounced off of the walls, this is electromagnetic signals, and it's going to be received. They were thinking about, again, physics. He said, all I have to do is to protect against the random effects that the channel adds. And he came up with the idea that you can add thoughtful redundancy in your information to protect against this. This is what we always do when we talk to each other. If we think the other person is not listening carefully, maybe you say the same concept twice or 3 times. And he showed that you don't need to do this too much. At that time, the conventional wisdom was the channel is noisy, I want to tell you something, I repeat it. And repeating means if the channel is bad, I repeat it a lot more. So very quickly, if the channel gets worse and worse, or if I'm really interested to make sure you know the answer, I have to repeat it many, many times, which means the rate of communication drops. And he showed that that's not necessarily needed. So you can work with channels. There is a fundamental limit that a channel can carry in terms of bits per second. It's a property of the channel, not the property of how I talk on. Characterize that, and then he showed you can always send at that rate. So it was like a fundamental, it's like a speed of light. There is a fundamental value of every channel. It provides you a bits per second, and then it became the sort of arms race for people to come up with methods to get to this fundamental value. Because his paper was a mathematical paper, said this number exists, there are random ways to do it, these are some things, and the joke was almost any random thing you do would get us to that fundamental limit, but anything that we think of is far from it. So in the 50s and 60s people tried, and in fact I was a graduate student when finally a team of computer scientists in France came up with showing that certain class of codes called turbo codes get us to the capacity of the channel capacity of the channel. So it was a long sort of, so in that sense he had a huge impact on the field. So in that sense it's very important. Now how it's related to modern day AI is that because these systems are information. When you look at images, you see a bunch of pixels, but you really are interested in whether this is a cat or a dog or a human or whatnot. So you are interested in some latent variable that is hidden from you, that is the information content of this. You're seeing some pixels. So you're basically asking yourself the similar questions as what Shannon posed. So for example, this year I have revamped our course on information theory. It used to be called Digital Communication 3. Now we call it the fundamentals of information processing and data analytics. So we are sort of looking at it from the perspective of inferring information, and a lot of that methodology comes behind it. Yeah.
So actually, my favorite part of Shannon's paper is it's often overlooked. It's where he makes a generalized statement. He says it's possible to view the entire universe as being nothing but information.
Yeah.
And if you think about that long enough, you'll lose your mind. But it's true. There's an awful lot to think about with that. But speaking of this, you spoke to issues of security and all that. I recently saw the documentary. I think it won the best documentary in 2019, The Great Hack. And I don't know how many of you might have seen. I highly recommend that everybody see that, The Great Hack. It really does expose, it brings up addresses a lot of important ethical issues with respect to the use of technology who owns technology, how it's used, and perhaps most importantly, what the social impact of that is. And so it seems, my impression is that in the security world these days, security is always it's addressing security in the small, which is how do we protect information for those who own it. But I'm wondering if you might speak to that, and also, like, do you think that more and more will be able to start talking about security in terms of the implications of its social impact,
Yeah.
what that means to our species?
That's true. So this is so big of a topic. One thing that I think is really happening as we speak. So California just passed a new set of privacy laws that makes your information on devices that you carry as extension of your body, right? So a company should guarantee that this information is private and is held by you, owned by you. They cannot use it without your permission. Now, this is good in terms of policy description. Unfortunately, there's a whole lot of really interesting unanswered questions in terms of technologically, how do we define privacy? How do I monetize privacy? How do I regulate the use of the data that has been collected? So these are really broad and important questions, and this is another area that I think we don't do as good of a job, but we should do better in terms of STEM education. Unfortunately, STEM education in the US is always perceived to be, you do this for industry partners or corporations, or sort of like the sort of main seller of your technology. And I always say, when people talk about privacy, I say, privacy, expecting Google providing privacy is like expecting Boeing providing, safety of the flight. You really need strong advocacy groups, citizen groups that are thinking about these questions, but also have the ability to translate it to technical expertise and come up with technical solutions. How do you regulate? How do you monitor? How companies are using? So these are really interesting questions, and I always tell my students, think about it. Think about the policy aspect. So there is also a very, very interesting questions about policy, and and I really think, as I said, there has to be more just natural, grassroots or groups that are interested in science and technology for that reason alone, because you cannot go with just policy. You can make this great, fantastic policy that you see in California, but you need somebody to tell the companies how they're going to translate the policy into monitoring.
So this might be a silly kind of non-major question, but when I saw the flyer and I saw what your specialty was, the way mesh networks were explained to me was as the same sort of thing that police use for their computers and their cars and so on. And I'm like, whoa, visual recognition and drones and mesh networks. I'm like, isn't there a little transmitter in every stoplight in San Diego? I'm like, how far down the pipeline is things like flying traffic cops that are automated and reading license plates and watching stop signs? I thought I'd ask.
No, that's a very good question, and that is exactly the question. I bring it back to the previous question, because I think the only difference, we know, for example, in other countries, that there has been less overseeing of this process. We know of monitoring crowds and finding people in the crowds and policing. So in some sense, the only way to stop that, there is really the technology is there to do many of these things. The only way to stop it is through policy, through participation in, the participatory democracy is the only way I think you can actually intervene it. There's no shortage of people who can actually figure these things out, as we see around the world, and even if we don't develop it here, it's easy to buy it from others. So it's really important. That's what I think touches upon privacy is one issue, but other issues of like how these technologies are used and how they're they become, it's true for all science and engineering. do the work of developing it, but really the use and ethics of it requires a bigger question. And I would say that's why, so my other sort of big passion in UCSC has been diversifying the student participation, and I think that's one of the reasons, like, who gets to be educated in this field is so critical exactly for those questions, who makes those decisions.
So you're saying the technology is already here?
Yeah, like if you want to fly something, I mean, like, yeah, I mean, these days, I mean, the technology has been there for a long time to do fly satellite that reads my handset, right? Like, the question is, who does that, right? Like, and I think that's the problem. And if you look at, like, the Snowden, you know, disclosures, the technology was there. It's just finding a person who is willing to say this is not okay is the rare one, right? I don't think it's
with what you said about the ethical questions that come up with AI, is there anything that you personally have on the warnings, fears, or anything on the quick progression of AI technology without laying down certain policies, ethical, and anything like that? Is there anything that you have?
You know, I feel like this is generically true with technology. I think AI is one such, you know, if you look at chemical industry, if you look at, like, there has always been these really deep ethical questions that come hand in hand with developing technology. And yeah, so there, as I said, just simple questions of fairness, who gets to be, you know, like they were talking about, like, assigning, for example, it's just simple things like,
But,
you know.
A lot of those other technologies, although the same ethical questions come up, the possibilities of the invasiveness of it was definitely not as great. So on that front, would you say that it should run as past technologies have, which I am for all open market and make a profit, but there are certain things that definitely scare me personally. You know, I don't want to be picked out in a crowd super easily, or my picture all over the internet.
I mean, I don't know if it's like picked up more than pesticides, or, you know, there has been the history of technology and science says that technology has always been misused for corporate interests and has been played down, like we know about the climate change. So is it more than those? I think it's just a philosophical, and then there's no point in arguing which one is the worst or which one is the right? But my answer is really we have to all be very vigilant about seeing both the development of it as well as regulating it and thinking these ethical questions. And my worry is that if you separate the two, you won't get the right answers. And right now, that's the effect that is very felt, is that if the system of education becomes too specialized for a particular group, it's even more dangerous. So the best hope you can have is, you know, diversify the participation, broaden the participation, and hope people like you guys, I might not be thinking about some of these, but the new generation comes in and they're thinking about, no, this is not acceptable, let's build a, you know, sort of both policy, from a policy perspective, but also technology perspective, a counter for them.
Thank you.
Yeah.
I think one of the quandaries or paradoxes that makes security so difficult to get a handle on, and perhaps will ensure that we never get an ideal handle on, is the issue of transparency. And the transparency can be a way of ensuring that that the use of information is not abused by certain parties. But then the question is, where do you apply the transparency? You know, what is transparent and what is not for who and in what circumstances?
Yeah.
And I think that's going to be an ongoing battle. You know, I mean, just, you know, people are going to be fighting for their opinion of what should be hidden and what shouldn't be hidden.
Yeah, no, definitely, for sure. I mean, I joke around, but this is a true story. So for the longest time in my life, I was very concerned about my privacy. I didn't ever sign up for, like, I don't know, cards at grocery stores, or like, I was like, I don't want anybody to know. And one night I was watching a TV show that I really liked on my computer, and I finished all the free ones, and the new season is there for 1999. And I felt very stingy. It was 10 p.m. and there was this link that says, click this for free access. I clicked, it asked for my name, for my information, and I entered it. I got one episode. I entered the rest of my information that I hadn't given to the first one, to the second. There were 3 episodes. I saved myself literally $1.99 with each click, and I undid 20 years of being really careful about, not 20, at the time, 10, 12 years. So another issue with privacy is these questions of access, and if you leave it, and this is the same with credit markets, and leaving it to consumers, you know, to decide and assuming that they're always going to make the decision. It's not true. You can be me, knowing about all of these, and in 3 clicks of a button, I received as many insurance ads and car sales and stuff in the next day as I had saved myself. So, you know, so I think it's the questions are very difficult.
Going back to what we could do actively right now to advocate for internet privacy, do you happen to know of any organizations or programs, perhaps at the university you work at, that I could actively do as a student, maybe today, tomorrow, to help progress that internet privacy education?
I cannot think of, so I can think of a couple resources, but I don't exactly know to give you the link, so send me an email. And I will dig that information up. One place that I know, the state of California, the legislature is always interested in people who do in science and technology, are interested in policy questions. So they have, at various levels, they have interest to give you fellowships or things, and you spend some time, I believe, in Sacramento, working with legislatures, and then, you know, as your students or volunteers. There are also on campus groups that are interested in these questions of privacy that I can get you in touch that are more on the policy side if you're interested on history.
This
side.
is for UC San Diego, right?
UC San Diego.
Okay, great. Thank you.
So I have a question in regards to like, what kind of math are you utilizing a lot of? And then when you're doing the programming, are you working on like architecture? Are you working like in assembly, or what sort of languages are you utilizing?
Yes, okay. So that's a great question. I use predominantly the mathematics we use is mathematics of randomness or probability, or if you want to impress. I'm a you know, foreign language speaker, so I really like it because I use this word very commonly in my research. It's called stochastic control, and many native speakers don't know what it means, so I really like it. It's just a fancy word for random control of random systems. So. And I joke, I have you know, use case for playing poker to all the way to actually building these AI systems in terms of the math. And in terms of programming these days, more and more, the students on my end and on the theory end use Python to do, because it's very high level. I joke that you can say please, and everyone has a command for please. But yeah, so but depends on how close you to the hardware you get. But the goal, hopefully the goal is that we will have the, you know, this automated circle that translates what you're doing to lower level languages much more transparently. Or any more questions? Yes. Oh, no.
Can I have your email address?
Yeah, it's very easy. It's my first name. I guess this is the only good thing about being a woman in engineering is that you get very good, easy email. Actually, there is another Tara faculty of engineering. So if you do it only at UCSD, she will get it. Yeah. so we can send you.
So I'm going to ask and answer a question. So is it possible to learn Python here at Mesa College?
Yes.
Yes, it is. There is a Python programming course, which is CISC 179. So if you're interested in that, you can take that in the fall.
Can you describe your daily routine at UTSB?
That's a good question. Depends on the day. On Tuesdays and Thursdays, I teach. And on Tuesdays and Thursdays, I give ride to my best friend's daughter to school. So I leave early and get to school maybe around 8:30ish or so. Look for parking, which is non-trivial on campus.
Here.
I could see from the construction that I would get sympathy. And then because I teach at noon, and so the morning is usually I try to block off for preparing my class. Does not matter how many times I teach a class, if I don't spend some time sort of organizing what I'm going to talk about, I invariably cannot do a good lecture. So it takes me, a non-trivial amount of time to prepare. And then I teach, and then after I teach, I eat at 2:30. And then I have office hours for an hour. And then I have usually meeting with my graduate students until 7:30ish or so. So that's my Tuesdays and Thursdays, much more focused on teaching. Mondays and Fridays are more alike, so I have a combination of meetings for various faculty stuff. Campus has a lot of committees. I am also representing UCSC's faculty in the system-wide, so UC's, there are 10 campuses, so there is something called a system-wide faculty senate where the UCs work on district governance, so the administrators and the faculty sort of make the final decision. So I have meetings of this sort mixed with research group meetings with my PhD students and undergrads and whoever wants to do research with me. And then Wednesdays, I try to block it off to do, because I'm a theoretician, I like to sit alone and I say TTT, thinking takes time, even though it's very invisible. You're felt like, and most of my research, I'm stuck. I'm not making progress. It takes 4 or 5 months to finally solve a problem, and if I don't spend the time, it will never happen. And I really like that sort of solitary part of research. So Wednesdays, I try to block the day off for a combination of writing things that we have done, and I have to do the writing part. Writing does not come easy to me at all, and it's a big part of having a faculty job at Research One University, so I do half of it in writing and half of it thinking. So I just try to solve. And when I say thinking, I usually reduce my problems to puzzles. So if you like math puzzles afterwards, stay and I'll tell you what are the very easy problems on the surface that have been unsolved and not solved by for many, many years by mathematicians.
Did you already discuss your work with lighting, the company? I think they make cameras, right?
Yes. So they're not, they're not working with me directly, so I can't tell you specifically, but we do a lot of work with various vision algorithms to process the data that they collect. That any camera collects, in particular with the drones that we fly. My students do a lot of sort of analytics around. You take an image, you try to sort of classify the content of it, and then use it for making flight optimization.
Doesn't that company provide cameras for any products in cars?
Which company?
Lytics?
Linux.
LYTX, I thought you said that was one of the big companies.
Lidus. No. The company that supports us is called Lidus. It's a company that provides a variety of technologies from, chips that you use for radar processing and image processing, and all the way to providing networks of radios that talk to each other, as well as
Is that LY?
LEIDOS. I should tell them. So
Okay,
I
so-
always tell them that the students don't recognize their name, and that's to their disadvantage, and they should support us more so that we can do the advertisement for them. And they should, in fact, support another student of ours for just the advertisement. Yeah, they're a fairly big company.
Yes,
US
they're very
based.
big. They're like one of the largest.
Yeah, but they're name recognition.
They do intelligence work. They're one of the
They
biggest
do a
contractors.
lot of subcontract work
They
with
would-
the military as well. But all- Any other?
Can you share any advice that you have for students thinking about preparing either for transfer to UC San Diego or another four-year institution, or if they decide to enter the workforce?
Office hours. How many of you do regularly go to office hours? Oh my God, very few. Please go to office hours. I myself didn't know what a great resource they were until I was a PhD student, and I sit in my office for hours waiting for students to come, and nobody comes. And it's very disappointing. This is the best way to learn. It's like a tutor time. So if you do not, so I always tell students, work in groups in engineering, isolation is the primary factor you would not succeed. People, unfortunately, there's this image of like you are going to be like so genius that sit at home and you're like solving all the problems. I've taught for almost now, 18 years. I have not seen that. Most students who are successful are plugged in, have friends, they talk about the work, then when they get stuck, they overthink it and then think it and think it until they learn from a new person, a different way of thinking about it. So I always tell students, for homework, the same thing. You talk to your colleagues and friends and in the confines of what is acceptable in every class's syllabus in terms of collaborating. But at the end of the day, separate yourself from the group, sit alone, and process the information, try to write down the solution. And that's where sometimes you think, I didn't understand, and that's when you should go to the office hours. And I don't know why the students tend to think professors are scary. I don't know what it is, but like I never get enough crowd in my office hours. And I would say, especially here, but especially if you transfer to one of the UCs, make sure that you take advantage of this to make sure that if in the case your group, either you're working or your life, cycle doesn't fit the sort of the traditional college campus life, that you take advantage of the faculty. That's the way to make sure that you're not isolated, you're not doing things alone. So that's my advice. So start here, where you already are here, you feel comfortable, start going to office hours all the time. Then when you come to transfer to one of the UCs, it will be a habit. You will just do it. The equivalence is when you go to industry, you feel also more bold to talk to people when you don't quite understand what's going on. So that's, I think it's really the difference between an A student and a B student is A students is not that they don't get hard questions, that they get stuck. But when they get stuck, they feel, this is where I'm stuck and I don't understand this one thing. So they have resolved this where their question is, and that helps a lot. And you only learn to get there when you have another person to sort of brainstorm with and tell them, I think this is where I'm not understanding, and sort of you get that one-on-one feedback.
So you work with drones that are flying around the side of rooms.
I do both, yeah,
You do?
both inside and outside.
But, so the inside drones, it's a more difficult problem, right?
Absolutely. They are blind. So the little drones that we have don't have a whole lot of sensors. So they don't know where they are. So yeah, that's the secret
What are your
sauce.
sensors? What sensors do they have?
They have a sensor that allows them to stabilize their height. So basically a sort of a proximity sensor to the ground. And they have a camera that stabilizes them. So actually it's a very, I said that's another question of control. So my students came to me and said, these drones are not stable. These were my undergrad students. And I said, what are you talking about? I've been working with them. They're super stable. So, no, they're not stable. When we put them in the room, they kind of like, go around. I was like, which room? Show me. So they take me to this conference room, and they fly the drone, and the floor is like completely one solid color. So because there's no feature, this poor drone is floating. So I had a banana in my hand and was eating when they came to my house. So I put the banana under the drone, and the drone stabilized. So it has a camera that looks down, and just like the one in the Science Museum. So those are the only two sensors. Unfortunately, the camera on the drone we don't have access to. Again, these are just because they're cheaper drones. They don't give us access to all of the sensing because they want to use the stability in a closed loop system. They don't give us the access to that camera. There's another camera that we can use to just view the environment. It's really hard with these angled cameras with that quality of camera to use the camera to do a lot of 3D reconstruction. You're looking at very small 2D images, and you have to build sort of the visual cognition of the 3D space, which is quite hard.
Yes, excuse me. I've been reading a couple of articles lately on people porting TensorFlow to much smaller processing platforms like microcontrollers and such. I was just curious about what you think about that.
So people nowadays do it. They take a model that has been designed and put it towards it. We would like to do this operation more automated. So yeah, so that's exactly the core of what we are promising to achieve. Is that right now the companies do this, they bring somebody who knows the platform and understands enough of what this neural net does, and then basically ports it or accelerates it on that platform. And we would like to do that in an automated fashion. We use some techniques from optimization and machine learning to go back and do that.
To that point, do you use Python for real-time control systems at all, or is that too slow?
No, that's too slow. So so all of the stuff I'm doing is at the time scale that makes sense. That's why the camera is not given to us in terms of access, because if they open it up to software, then the delay.
Yeah, they get a weaponized drone so you go hunting for your truck.
They have, unfortunately, weaponized drones, as we all know. Not in my lab. And not for trucks, that's what I do.
That would be wonderful. Any last questions or things that you can share? Can we get Dr. Javidi?